Hello, this is video number 2 on projectile motion. We've hopefully mastered horizontal projectiles so far. If not, that's fine, we'll get there. But today we're going to move on to projectiles that are projected at an angle. So instead of being horizontally projected, like we just looked at, they're now going to be projected on an angle upwards, angle downwards. Which changes things a little bit, not very much, but we're going to look at that. So let's talk about it. So let's start with a reminder of the things that make projectile motion, or characterize projectile motion, I should say. Remember that acceleration in the y direction is always equal to negative 9.8 meters per second squared. And because there is acceleration in the y direction, that means we use kinematic equations in the y direction. Remember that in the x direction, Vx will be equal to some constant number. There is no acceleration. Acceleration is 0 in the x direction. And because of this, we use V equals d over t in the x direction. A few other things. Remember that at the top of the arc, Vy equals 0. Which is very useful for us because if we know that, then we can figure out a lot of things about the very top of the arc. So we'll use that to our advantage. Now, we're going to talk about projectiles that are fired at an angle to the horizontal today. So here's an example that we're going to work through. A ball is thrown with an initial velocity of 20 meters per second, 37 degrees above the horizontal. I wish I could throw a ball at 20 meters per second. That's pretty fast. We're going to determine a bunch of things to illustrate all the different things that you can do with a little bit of knowledge of projectiles. First, we're going to find the maximum height of the ball. That is the vertical height to which it rises once it reaches the peak of its arc. We're going to find the time of flight. Remember from last time, that is the total amount of time spent in the air from when it is thrown or projected or whatever you want to call it till the time it just starts to make contact with the ground. We're going to find the range. Remember that the range is the horizontal distance that the ball moves. Yes, the ball is moving up and down as it does this, but we're more concerned about how far horizontally does it make it. How far can this ball go? We're going to find the ball's velocity. At its maximum height. We're going to find the ball's acceleration at its maximum height. And last but not least, we're going to find the velocity of the ball at t equals 1. One second, I should say. So 1 second into its flight, what is its velocity? A good starting point for any projectile motion question is to start with a sketch of the object's path. So maybe let's do that right now. So we've got our ball, and we're going going to start by drawing the ground. And the ball is going to be projected at an angle upwards. That angle we said was 37 degrees above the horizontal, with an initial velocity of 20 meters per second. 37 degrees above the horizontal. That ball is going to follow a parabolic path until it impacts the ground some distance right there. So that's the path it's going to follow. Here's the top of its arc. Remember that maximum height is achieved at the top of the arc, and we'll look at how do we figure that out in a second. Okay, so let's get started with this. A good first thing to do is to realize that because this ball is being projected above the horizontal, there's a portion of the velocity that is acting upwards and a portion of the velocity that is acting in the x direction. So those are two important things to start with, because once we determine the x velocity to start at that point, that will always be the x velocity. So here is the overall velocity. It's made up of two smaller vectors, the x component and the y component. This angle is 37 degrees, and this is 20 meters per second. Here's Vx, here's Vy. Sine 37 is going to be Vy over a hypotenuse, which is 20. So Vy will be equal to 20 sine 37. Again, like always, this would be a good value to, if you have a memory function in your calculator, to throw that in the memory function, because I'm going to keep writing 20 sine 37 to not round off a whole bunch of digits, but that can also be a little bit annoying to have to write 20 sine 37 all the time. But I'll leave that up to you. Similarly, if we're looking at the x direction, Vx will be equal to 20 cos 37. By similar reasoning, I'm not going to show that initial step there. So this x velocity that we just found, that will be its x velocity at all times. And this y velocity is the one, constant t. This y velocity will be the one that changes. As time goes on, it will, right now it's positive, it's acting upwards. It'll slowly but surely go to 0. Once it reaches 0, then that's the top of its arc. And then it will be going in the negative direction until we get to this point where the y velocity will be negative 20 sine 37 because of this nice symmetrical path that it follows. So question number 1 is the maximum height to which the ball rises. In order to find that, we look at what we have and what we're trying to find. We're trying to find h, which is a displacement. So d is our question mark. And if we're talking about d in the y direction, we're talking about a vertical displacement, that means we have to ask ourselves specifically about the y direction. What else do we have? In the y direction, we know that velocity will always be negative 9.8 meters per second squared. We now know that at the instant that the ball is thrown, here's its y velocity. So that is the initial y velocity. It's equal to 20 sine 37. We need one more piece of information in order to use our kinematic equations in the y direction. We do know that at the top of the arc, the significance of that spot is that Vy is equal to 0 at that point. So we can use that as one of our pieces of information. Vyf is equal to 0. So dA, Vi, and Vf, that sounds like Vf squared equals Vi squared plus 2AD. Vf is 0, because we're talking about that point right there. And in the y direction, yes, it is moving the x direction. Overall velocity, net velocity is not 0, but in the y direction, velocity is 0. So 0 equals 20 sine 37 squared plus 2 times negative 9.8 d. which is what we're trying to find. Now is probably a good time to evaluate 20 sine 37 if we're going to be squaring it. So here we go. 20 sine 37 is 12.04 if we round to 2 digits. And we're going to need to square that. So I'll square that right away. So some big number. I'm going to keep that in my calculator. 0 equals 144.9. I'm going to write it rounded, but I'm going to keep the number in my calculator. Plus negative 19.6 times d. We're going to subtract 144.9 from both sides. We'll end up with negative 144.9 equals negative 19.6d. So we're going to need to divide both sides by negative 19.6, and that's where we're going to get our positive value for d, because if it's traveling upwards, we should get a positive value for it. So I'm going to take negative version of my answer, just doing that to get my negative sign, and I'm going to divide it by 19.6 negative. Maximum height of the ball is 7.39 meters in the positive direction. So there we go. The second question here is the total time of flight. Again, like we talked about last lesson, remember that if we're looking for time of flight, we're looking in the y direction, because the y component is what controls how long it spends in the air. It just keeps on chugging away in the x direction, but the y direction is the one that changes and then becomes negative as you move into the second half of the arc. So that's what really determines how long it spends in the air. You have two options here. You could use the same information we used here, compare the starting point to the midpoint, and because the path is symmetrical, however long it takes to get to the top, it's going to take that long to get to the bottom. So however long it takes to get here, double that and you have the total time of flight. Option number 2 is we can compare the starting point to the ending point instead. Now the difference here is if we do compare the starting point to the ending point, and we're looking for the amount of time spent in the air. At the beginning, this projectile has a y velocity pointed upwards, and its magnitude is 20 sine 37. At the end, because the path is symmetrical, this object has the exact same magnitude of y velocity pointing in the opposite direction. So its y velocity at the end would be negative 20 sine 37. We're going to do that second option. We're going to compare the starting point to the ending point, just because we want to pick one. You could just as easily compare starting point to midpoint and then double it, and that would be fine. So for part B, when we are looking for the time of flight, if we're comparing starting point to ending point, meaning very start of the arc way back here to the very end of the arc way over here, then what that means is Vyi will be equal to positive 20 sine 37 Vyf equals negative 20 sine 37. Because the path is symmetrical, that means it will have the same magnitude but just opposite direction. Because we're looking in the y direction, we know that AY will be equal to negative 9.8 meters per second squared. And we're looking for t, the amount of time spent in the air. So with our two v's and acceleration and time, that is an a equals delta v over delta t, which expands to Vf minus Vi over delta t. That's this question, or this kinematic equation that we're going to use. A is negative 9.8. Vf is negative 20 sine 37. Vi is positive 20 sine 37, so that's minus positive, so minus 20 sine 37, over a time, which is what we're trying to find. I'm going to multiply both sides by delta t. We'll end up with negative 9.8 delta t equals, and I'm going to simplify this. If we have 20 times sine 37, or I should say negative 20 times sine 37, and we subtract another 20 sine 37, we end up with a grand total of negative 40 sine 37. That only works because we have sine of the same angle in both cases. It's multiplied by a common term in both cases. So delta t will be equal to negative 40 sine 37 over negative 9.8. So 40 negative sine 37. We're going to divide that by 9.8 negative. We end up with 2.46 seconds for the total time of flight. You should get the exact same value if you were to work through it, finding the time it takes to get from the beginning to the midpoint of the arc, and then doubling that result. Part C, we're now looking for the horizontal range of the projectile. I'm going to slide this up a little bit. Remember that when we look in the x direction, because ax is equal to 0, v equals d over t applies. We know that Vx is constant all the way, so that x component of velocity that we found way back here, this is still going to be its x velocity. In fact, that'll be its x velocity everywhere throughout the path of the projectile. We also know the time of flight because we just calculated it. So if this object is moving at the same velocity for that whole 2.46 seconds, we can figure out what the horizontal range is. So Vx is equal to 20 cos 37. Dx is what we're trying to find, and t, 2.46. I still have that number for time in my calculator, so I'm going to keep that there, and I'm going to multiply it by 20 cos 37 to end up with a horizontal range of 39.24 meters in the positive direction. Part D, we're looking for the velocity of the projectile at its maximum height. So this is where we have to go back and we have to look at what do we know about that top of the arc, what's significant about that point. The significance of that point is Vy is equal to 0 at that point. Now what that means is, as the ball is traveling through its path, it's at its maximum velocity right here, just as it leaves the ground, and as the velocity starts to go entirely in the x direction, the velocity is getting smaller, 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 until at the very top, the velocity reaches its minimum point. And since Vy is 0, Vx never changes. At the top of its arc, the velocity of the ball is momentarily equal to Vx, 20 cos 37. So at the top of the arc, all velocity is in the x direction, since Vy equals 0. Therefore, velocity at that point will be equal to our Vx, which is, let me see here, 20 cos 37. And if we were going to get the numerical value for that, we would get 15.97 meters per second towards the right or in the positive direction as drawn. Part E, we're looking for the acceleration at the maximum height, so again at that top of the arc. Now, if we are looking for the acceleration at the top of the arc, let's consider the fact that everywhere throughout the arc, acceleration is the same. At all times, this ball has an acceleration vector pointing downwards. It doesn't matter where it is in its path, whether it's here, 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 acceleration is always negative 9.8. Even at that point where y velocity is momentarily zero. There's a brief moment in time where velocity is zero, but that doesn't mean it's not accelerating. That just means for one brief, imperceptible moment of time, velocity is zero. It is still accelerating at negative 9.8 meters per second squared. So after that moment of time is gone, it continues to accelerate. It will now have a negative velocity. So that means I could have asked you at any point in the arc, what is the acceleration at any point? And it will always be negative 9.8 meters per second squared in the y direction. The last question here that we're going to look at is the velocity of the ball at t equals 1 second. Now, t equals 1 second is a very arbitrary point. It's somewhere in the arc just before you reach the halfway point. We already know that the total time of flight is that 2.5 seconds. So if it's 2.5 seconds to go the whole distance, that means it's 1.25 seconds to reach the top. So 1 second is like, you know, over here somewhere. Exactly where is difficult to say. So you might be asking yourself, how can we find the velocity at that point if that's the case? Well, the answer is, we know the x velocity is always the same. Everywhere along the entire arc, velocity in the x direction never changes. In the y direction, if we know the initial y velocity from here, we know the time elapsed is 1 second, and we know the y velocity is always negative 9.8 meters per second squared, we can very easily find the y velocity. Knowing the x velocity and the y velocity, we can use vector addition to figure out what is the overall net velocity at that point. So first of all, we know Vx is always equal to the same thing. In our case, it's 20 cos 37. But we need Vy to construct our triangle by vector addition. So here's the things we know. We know that acceleration in the y direction is always equal to negative 9.8 meters per second squared. We know that initially, if we're comparing to that initial point where the ball is first launched, Vyi is equal to that original 20 sine 37 in the positive direction. If you want to include the positive, you can, but that's usually reserved for final answers for showing direction. We know the amount of time elapsed is 1 second. And we're looking for Vyf at that point. What is the velocity of the ball at that point in the y direction only? Just like before, this is going to be A equals delta V over delta T, which we can expand delta V into Vf minus Vi over delta T. Negative 9.8 is our acceleration. Vf is our unknown in this case. Vi is positive 20 sine 37, so minus 20 sine 37 over top of 1 second. So that 1 is kind of nice because the 1 will just disappear. We end up with negative 9.8 equals Vf minus 20 sine 37. We add this 20 sine 37 to both sides to get our answer for what Vf in the y direction will be equal to. So we have negative 9.8, and we're adding 20 sine 37 to both sides. to give us a y velocity of 2.24 meters per second in the y direction. I'm going to hold on to that number and not clear it. So that means at 1 second, we have a y velocity of positive 2.24 meters per second. X velocity is that 20 cos 37. So let's draw our triangle. We have an x velocity pointing that way. We have a y velocity pointing that way. Y is significantly smaller than x, so I'll just try to draw it somewhat to scale. Here's Vy, sorry, not Vy, Vx. Here's Vy. And here is V net, overall net velocity. Again, we always need that angle. So Vy is that original, or that number that we just calculated. So 2.24 meters per second in the positive direction. Vx is our 20 cos 37. So like usual, we're going to use Pythagoras to find this side, and we're going to use tan to find this side and this side. Or sorry, not to find that side and that side. Use tan with this side and this side to find the angle. We'll start with the magnitude. V net squared. It's the hypotenuse, so that's our C side. Our A side and our B side are those two. We're going to square those as well. Okay, we need to add all this stuff together. Here's that original value from the value of Vy. So I'm going to square that. I'm going to add to that 20 cos 37 squared. To give us this, 260.1. That's equal to our V net squared. So V net will be the square root of both sides. (16.13 meters per second). So that's the magnitude, but now we need the direction. We can see the direction is above the horizontal, because this picture that we've drawn is a side view. So that means an angle like this would be above the horizontal. So we need to know how many degrees above the horizontal though. Tan of theta will be opposite over adjacent. So 2.24 over 20 cos 37. So here's that number again, divided by 20 cos 37. Be careful with your brackets here, because if you go x, or if you go 2.24 divided by 20 times cos 37, but don't include brackets, you're not going to get the right answer because of order of operations. So make sure you keep everything in the denominator in brackets to avoid that problem. So tan of our angle is that. 0.14 and then like a bunch of zeros, but that's fine because we're just going to do the inverse tan operation to that to give us 7.97 degrees. So our overall velocity, magnitude and direction included, is 16.13 meters per second, 7.97 degrees above the horizontal. That is the overall velocity of the ball at that time. Another note to make is that you could just as easily do this with position. So instead of finding net velocity, if you were now trying to find what is the position of that ball at 1 second at that wherever it is, somewhere just before it reaches the top, you could just as easily find the position using the same method. Use the x direction and the fact that the x velocity is always this to find, okay, so if it travels that fast for 1 second, where is it in the x direction? Use kinematic equations in the y direction. You know that this is the initial y velocity. The time would be 1 second. Gravity is negative 9.8 meters per second squared, so that's our acceleration. And we're just trying to find d. How far vertically does it travel? And using the exact same method, construct a triangle, you could find the exact position and the direction as measured from that initial throwing point. So that's something that I'm not going to show here, but you could do that very easily, and it would just take the one extra step of calculating what is that x position. So that is projectiles projected above the horizontal or below the horizontal. We only showed an example above, but below would be exactly the same. Just means initial y velocity would be in the negative direction. So hopefully this has been helpful, and we will talk about it more in class if you have some difficulties.